This is the 6th video in the revision tutorial series for EDEXCEL P3. Today we will be looking at X-rays. In today's video we will be relating X-ray ionization levels to frequency and energy. We will look at X-ray creation, we will look at how X-rays are used in medicine, and finally we will calculate the accelerating voltage, the kinetic energy and the velocity of electrons in X-ray creation. From the first video of this series we looked briefly at X-rays. So to refresh our memories, X-rays are part of the EM spectrum. They have a high frequency and have high energy. They are very ionizing, which can cause cancer. X-ray images, such as the image here, are possible because they are absorbed by thick, dense tissue like bone, but easily transmitted through soft tissue. This means that the areas where the X-rays are absorbed will appear on the X-ray scan. X-rays are then formed through collisions with metal targets behind where the X-ray has been taken. X-rays can be used to diagnose and treat some medical conditions, including tumours in the body. For example, in CT scanners, the X-rays are used to build up an image by photographing each layer of the body at a time. This gives us a 2D slice through the body. However, we can also use them in fluoroscopes, where the patient is placed between an X-ray device and a fluorescent screen in order to look at tumours and damages to the body. Fluoroscopes can also be used to see moving images of the internal structures of patients. They can be used to investigate problems with the digestive system. We will now look at how X-rays are made. So to look at this in a little bit more detail, we have our X-ray machine here. In a few slides' time we will look at what exactly is happening inside this machine. The X-rays are transmitted out and absorbed by the dense parts of the patient's body. In this case we'll be looking at the bones, and then this photographic plate or digital detector will pick up the transmitted X-rays. This will then produce a radiograph where the white indicates the dense parts of the body and the grey indicates the less dense areas of the body, in this case the soft tissue in between the ribs. Inside the X-ray machine we have a process called Thermionic emission, which uses an evacuated tube. We will look at this on the next page. Inside the X-ray machine we have a device known as an evacuated tube, in which two electrodes are found, the cathode and the anode. The negative electrode, the cathode, is a wire filament that emits electrons when heated. So the role of the heater is to emit the electrons. This process is called thermionic emission, and the wire filament is called an electron gun. When there is a large potential difference between the two electrodes, these electrons are accelerated from the cathode to the anode. So, the potential difference between the anode and the cathode is used in order to accelerate these electrons. Finally, a vacuum is used in order to ensure that the accelerated electrons do not collide with any other particles. This movement of electrons from the cathode to the anode is the equivalent to an electric current. When the electrons collide with the metal anode, kinetic energy is transferred into thermal energy, hence thermionic emission. At this point, some of the kinetic energy is also transferred into X-rays. In order to produce X-rays with more energy, a higher potential difference between the two electrodes will be used. These X-rays will be more penetrating and more ionizing. Because we can alter this accelerating voltage or this accelerating potential difference, we can use this to calculate the speed of an electron. As we said, the beam of electrons through the tube is basically an electric current, because current by definition is a flow of charge. Each electron, as we know, has a negative charge. Charge is measured in coulombs, or C. So we can work out how much current flows in a circuit using the below equation. We have current, which is I, over the number of charged particles per second, N, times charge, which is Q. We will now look at 3 examination style questions. Here are 3 example questions from the exam. I want you to pause the video and attempt to answer these 3. Remember to use the equation current equals number of electrons per second times charge. So for question 1, you should have an answer of 1.6 times 10 to the minus 13. Question 2, you should have an answer of 8 times 10 to the minus 10. And finally, question 3, you should have an answer of 6.25 times 10 to the 16. We will now look at how to use charge to calculate both the velocity and the voltage of an accelerating electron. In order to calculate the speed of an electron, we can look at the electrical work done. This means that we can put together the equation of charge times voltage equals half mv squared, where half mv squared is equal to the kinetic energy. We will now look at this equation in more detail. In order to use this equation, we need to be able to rearrange it. So our equation is charge times voltage equals half mv squared, where we have E, which is the charge of the electron, capital V for voltage, and then half mv squared, where m equals mass and v equals velocity. So, in our question, we have a high voltage accelerates an electron from rest to a velocity of 4.0 times 10 to the 7. This is going to be our velocity. We are then given the mass of the electron, which is 9.1 times 10 to the minus 31. This is a constant, as well as the charge of the electron, again a constant, at 1.6 times 10 to the minus 19 coulombs. The question then asks us to work out the voltage of this electron acceleration. We now have all of the numbers to plug into our equation. This gives us our charge, 1.6 times 10 to the minus 19, times our unknown voltage, which equals 0.5 times our mass, which is 9.1 times 10 to the minus 31, times by our velocity, which was 4.0 times 10 to the 7. It's important to note that it is only the velocity that we will be squaring. So if we do that first, we will get 1.6 times 10 to the 15. We can now solve the equation on the right hand side by doing 9.1 times 10 to the minus 31 times 1.6 times 10 to the 15, and then timesing that by 0.5. This will give us 7.28 times 10 to the minus 16. In order to work out V, we now need to divide both sides by 1.6 times 10 to the minus 19, which will give us a final answer of 4,550 volts. Remember that you get a calculator in the exam. Also remember to use the brackets. The reason the brackets are there is that it ensures that the calculator carries out the calculation correctly. It also means that you are fully aware of which part of the equation relates to which part of the question. We will now look at a second examination question. In this question, we are given the kinetic energy gained by each electron. EV equals half mv squared and also equals KE, where KE is equal to the kinetic energy. I want you to pause the video and attempt to calculate this question. In this question, you are looking for the overall accelerating potential difference, so the voltage, so the answer is 60,000 volts. In this third and final question, which is the hardest version of the question they can ask you, you are now given a supplied voltage. We've got the potential difference, which is 100 kilovolts or 100,000 volts. It's now asking for the velocity of the electron during the thermionic emission, and we have the mass and the charge. So once again, we have the charge, which is 1.6 times 10 to the minus 19. This is going to be E. This time we also have our 100 kilovolts, which is our voltage, which is V. Remembering that 100 kilovolts is equal to 100,000 volts. We have also been given the mass, which is M, at 9.11 times 10 to the minus 31, and this time we will be looking for V, which is our velocity. So when we plug our numbers in, we get the following. So we have 1.66 times 10 to the minus 19, our charge, times our 100,000 volts, which is our voltage, which is equal to 0.5 times 9.11 times 10 to the minus 31, which is our mass, and then finally we have our V squared, our unknown velocity. Straight away, we can work out the left-hand side of this equation, where we will do 1.6 times 10 to the minus 19 times 100,000, which will give us 1.6 times 10 to the minus 14. We can now divide both sides by 0.5 in order to remove this 0.5 times, which will give us 3.2 times 10 to the negative 14. We can now further rearrange the equation by dividing both sides by our 9.11 times 10 to the minus 31, which will give us 3.51 times 10 to the 16 to 2 decimal places. We can now rearrange the equation one final time, this time doing the square root on each side in order to work out V, which will give us an answer of 187,419,942.7, which we can then finally put into standard form to give us an answer of 1.87 times 10 to the 8 meters per second. Both the answer in standard form and the answer in long form are correct unless the question specifies for one or the other. This concludes today's tutorial video. In the next video we will be looking at 2 more uses of physics in hospitals when we look at ECG and pulse oximetry.